What if I were to tell you that there is a way to visualize a differential equation? A way to turn it from an opaque equation that's hard or impossible to solve into something you're seeing here. And what if I were to tell you that viewing a differential equation like this can give physicists and engineers a great insight into the dynamics of real-world systems? In this mini-series, I plan to teach the basics of nonlinear dynamics, so let's get started. To begin with, differential equations are everywhere. They're used to model anything from the growth of bacteria in a test tube, to the synchronous nature of flashing fireflies, to the orbits of planets around a sun. In this video, we're going to look at the first-order differential equation dx dt is equal to a half x squared minus 2. This equation looks harmless at first. After all, we can solve it. With a little use of integration, we can get x as a function of time. But there's two problems. Firstly, the solution doesn't immediately give you a qualitative idea of the dynamics. Secondly, what if the equation was way more complicated? It might not even be solvable. What then? Let's look at this another way. I'm going to plot dx dt versus x. In our example, it looks like a parabola. If we think of x as the position of a particle, then dx dt is the velocity of that particle. That means that these regions are where the velocity is positive, and this region is where the velocity is negative. Another way this can be represented is by using vectors. Here, each arrow corresponds to the velocity at each position. It's helpful to think of these arrows as a fluid that can push or pull a particle in one direction or the other. Okay, now we can visualize the solution with different initial conditions. For example, if x equals 0 when t equals 0, then we would notice over time the particle would move to the left, approaching this point minus 2, 0. Likewise, if the initial condition was here, then we'd notice the particle would move to the right, approaching the same point, minus 2, 0. But if we started here, then we notice the particle will fly to the right, approaching infinity. The advantage of viewing the differential equation like this is that it gives us a qualitative understanding of the dynamics of our system. Specifically, it gives us information about the stability at these points of zero velocity, which are called fixed points. Notice, the slope of the curve tells us what we need to know. If the slope is less than 0, like it is at this fixed point, then we'll call this point stable. It's stable because if the particle ends up at any small perturbation near this fixed point, it'll be sucked towards it. The other fixed point is unstable because it has a slope at this point greater than 0, meaning that any small perturbation from this fixed point will make the particle explode away exponentially fast. This technique is called linearization because we approximate the curve as a straight line at this point. Now, if you want to see a formal proof behind calculating fixed points, how linearization works, and the classification of stable versus unstable fixed points, I've made another video here. And there we go. We've briefly shown how to visualize nonlinear first-order differential equations. By thinking of the equation as a particle in a vector field, we can develop a useful qualitative understanding of the dynamics of our system. But wait, what happens if we have a second-order differential equation? What do we do then? Well, we'll talk about that next time.